Hello, good afternoon, good evening, everyone. Welcome back to Particle Physics for Teachers. This session, we're joined, or it will be led by Jesus Porta Pelayo, who's in charge of outreach at CEMAT, which is a national laboratory in Madrid. He's been on the CMS collaboration for about a decade and a half. I met him in May, and almost as soon as I met him, I invited myself to a course he was running over the summer, and he welcomed me with open arms. One of the things he showed with the muon telescope in the basement of his lab that he works with kind of opened my eyes to part of gas detectors. I was familiar with some of the concepts before, but because I learned a lot from him, I wanted to share that with everyone. So I was really eager to invite him on. So I'm thrilled to invite or welcome Jesus. Thank you again for joining us for this session. It's great to have you along.
Thank you very much, Michael. The pleasure is all mine, and thank you for inviting me to be part of this great course. Hi, everyone. Well, Michael already introduced me, but let me introduce myself again. I'm Jesus. I'm right now in my lab in Madrid at CEMAT, which is a national research institution. It's actually probably the second largest research institution dedicated to this field in our country. And I am also I'm a physicist. I'm a particle physicist, and I've been working at the CMS collaboration for not a decade and a half, almost 2 decades and a half. Look at my gray hair here. I am one of the fathers of the detector, and this is something you will see later. Let me share my screen so we can start telling you about. So when Michael invited me to take part in this, hide the controls here. To be part of this course, I had a doubt on how to what to tell exactly, what could be my story, what could be my part, what can I offer you as a new point of view in the context of this course. And after seeing what my other colleagues have presented in the previous lectures, I decided to go for telling you more or less the chronological story of what a particle detector is and how it comes to be, and then I will show you one in operation. This is here you are. This is what I'm planning to show you today along the afternoon. First, I will provide a little bit of context of what you're going to see this afternoon, compared to what you have seen already in the previous sessions with our colleagues, especially with Steve and Marco, that already showed you some first concepts of particle detectors. And the first course and the main course will be, as I said, the story of the detector I've been working for more than 2 decades now, and you will see that one in operation. As a dessert, if we have time, I will tell you a little bit of my ideas of what can you do with particle detectors of this kind at school. That's probably what you will be more interested in. So you have heard a lot about detectors. I'll try to provide as briefly as I can a little bit of context to put everything in, at least to clarify your mind in this sense. Probably you will be asking yourselves, this guy is gonna speak about detectors again? This is the 3rd session, at least, that you've had about particle detectors. I'll try to do something different, but yes, we have to talk about detectors, and this is the idea of putting this in context. Just a few ideas, 4 ideas to give you the fundamentals of particle detectors. Might sound stupid, but why do we use detectors for? Detectors are used to detect. We need to communicate with nature and with the smallest pieces of the universe, and those are the fundamental particles, things that are smaller than an atom. We need to communicate with them by measuring their kind, measuring their properties, and measuring what they do and how they interact with each other. And that's why we use detectors for. These are our eyes to the nature and to the world of subatomic particles. And the difference between our field and other fields, everybody, I mean, every science domain has their own machines and their own devices to work with and to communicate with the nature. But the difference in our case is that, consider this: we are measuring particles, but the way we use the way we need to interact with these particles is by their interaction with another type of matter. So it's particles interacting with particles, matter interacting with matter. In this way, the detector itself is part of the physics we're trying to do. So it's more than just developing a machine to observe nature. It's part of the science that we're trying to do, and that's what makes it interesting. The way we use them is by using the interaction of these particles with matter, with the material that they are traversing. And that, of course, leads to a vast variety of different technologies that we can use to detect the particles. We can have ionization, we can have nuclear interaction, we can have quantum effect, we can have bremsstrahlung, we can have pair production, and all these type of different interactions that we can experience. And for each one of these detection techniques, there is a different technology that we can use to see these processes in nature. And without detectors, that's why we are always so pushy for detectors and trying to show us what the detectors mean to us. The foundations of modern physics, where the development started when we started developing the first particle detector. So the evolution of this domain has gone hand in hand with the development of the detectors and the detection techniques. A little bit of prehistory of this particle detector. At the beginning of the 20th century is when we used the first detectors in the classical sense. They were the first particle physics experiment that we had. The first collision, the particle collision experiment, if you want, in my view, Rutherford experiment. Think about it. Rutherford, what he did was using gold foil, and he collided particles from alpha particles from a radioactive source with the particles of the gold foil. So it was a particle collision. And then around the collision point, he put a photographic plate. So this was a collision experiment. It was slightly more modest than the ones we are doing now, but it was the same concept. And these were the first detectors in this sense, if you want. They were photographic plates, scintillation strips. But the first imaging detectors, the first detectors that were used to view the individual particle tracks, and for the first time recognize that it was caused by a particle, it was the cloud chamber. The cloud chamber was developed by Charles Wilson. He obtained the Nobel Prize in 1911 for it. Anderson later on, he discovered the positron used in a cloud chamber, and he was also awarded the Nobel Prize. The bubble chamber, Marco explained you in details how it worked. I'm not going to go into detail, but Donald Glaser also obtained the Nobel Prize for that. The discovery of the neutral kernels that was done in a bubble chamber also set the basis for the electroweak theories and the discovery of the ZW bosons that were also awarded the Nobel Prize later on. So just to put in context how important the development of detectors in the world of physics is. There were other there were other techniques like the nuclear emulsion developed by Marietta Blau in 1923 that were used in the same sense. They were used to view the tracks and the interactions of individual particles. She didn't win the Nobel Prize. Don't ask me why. Later on, Powell discovered the pion using the technique of Marietta Blau, and he got awarded the Nobel Prize. I'm not going to say it was discrimination, but it's fill the blanks. But all these detectors that I have shown you so far, they were used as a way to view the tracks of individual particles. This is nice. This is very beautiful because you can actually see the trajectory of a particle. But that's not practical because you cannot, in nowadays world, when we are trying to view many, many different interactions that happen very, very frequently, we need something that doesn't require us watching and checking the pictures and the images of the detectors constantly. So the modern detectors are nowadays based on something else that was developed later on. Those were the electronic detectors. So instead of viewing, observing a picture of an image of the particle you want to see, you need to transform the interaction of that particle in your material into something that you can measure in an electronic circuit. So a pulse, a pulse of charge that you can actually measure and transform into the signal. The first detector of this kind were the electroscopes, in which Victor has discovered the cosmic rays, also a Nobel Prize. And the first actually detector, modern detector, if you want, is something that you all probably know, is the Geiger counter. You've probably seen in movies and in science fiction, this when the guys go around with a detector, beep, 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 measuring radiation. That's a Geiger counter. What is it? It's a tube filled with gas with an electric field. So because you put a high voltage in several components in this tube. When a charged particle traverses that tube, it ionizes the gas, and the ionization products are collected in one of the components. And with that high electric field that they have, they create a pulse of charge. And that can be measured. You put it in a circuit, you put it in a beeper, and then you have something that tells you that the particle has crossed the detector. That was the first of many, many, many other detectors that we have nowadays, modern electronic detector. Geiger didn't win a Nobel. He was a Nazi, so I'm kind of happy he didn't. Sorry. And as I was saying, that's a little bit of prehistory of the detectors. As you can see, the first detectors, the first modern electronic detectors were based on gas. So the gas was the material that was used to cause the interaction of the particle, and the products of this interaction were then collected and measured. Nowadays, we have not only gas, we have solid-state devices, we have novel gases, we have scintillators that instead of producing ionization, they transform the ionization into light that can be collected. We have also devices to collect this light and measure it. Those are the photodetectors and many other different families of detectors, if you will. How are we using them nowadays? You know the particle colliders already. You visited virtually Atlas with Steve a few days ago. So you know that we use them. We use these layers of detector to observe the products of the collisions of particles in the center of that detector. So this is one of the uses. But the particles do not only come from collider experiments. We can have many other different experiments that try to measure, for instance, neutrinos that come from different sources, nuclear reactors, from the sun, also from accelerators. We can put detectors on Earth trying to measure hypothetical particles of dark matter. Supposedly, we are floating in a cloud of dark matter, of cold dark matter. That might be true. That might be one of the hypotheses. So we place big isolated detectors here on Earth, and we can try to measure them. And also, the third option is looking above. If you think what telescopes are particle detectors. They are measuring light in different wavelengths, but they're also a particle detector. They're measuring photons. They're photodetectors. It's the same technology, depending on the energy of the light, the energy of the photon that you're trying to measure. You will have different techniques. We have also telescopes on Earth that measure the interaction of very high energetic particles that interact with our atmosphere, and all these products are measured. So we are trying to explore all different possibilities that allow us to connect and to know a little bit better nature. And these are the uses that we are giving them for basic research, but there are so many applications behind that. Mainly medical applications. If you go to have an X-ray or to have a PET scan, these detectors that they are using to form these images are the same type of particle detectors we're using in collider experiments and in other experiments. So
And just to jump in with a quick interruption on PET scans, because some of the teachers will be eager to hear if or when I scheduled the uh, PET PET session with Sarah Scholing, who developed a virtual lab for that. Unfortunately, she wasn't available in December, so that'll likely come if I do a deep dive series on medical particle physics in the new year. So unfortunately, that one's not being added. So I broke my promise that I made in the beginning when I said she said she'd do that session, but I did say we didn't yet find a date, so everything was tentative. So sorry about that. Oh, and while I'm interrupting, just we forgot to mention in the beginning, everyone please ask questions as they come up. Jesus isn't shy. Feel free to use your microphone if you're not shy either, or add anything in the chat, and I'll interrupt when I find it's an appropriate time.
Yeah, thank you, Michael. Please do. Don't hesitate interrupting me if you have any doubts or whatever. If you are too shy to do that with an open mic, just type it in the chat and Michael will read it out loud. But to me, it's perfectly fine, whatever you prefer. Perfect timing for the interaction, Michael, because that was that was the end of my appetizer. Now I'm going to talk to you about about my baby, of course. So far, was just a general introduction, but as an example, I want to show you how a detector is conceived from the very beginning to the very last, not the very last, but at least one of the last stages of its life. And there, I'm going to tell you the story as a tale of the CMS drift Tues. That's the detector I've been working on. What is this drift Tues? Let's go back in time. Let's go back to 1980, so many years ago. Anya described you the standard model. This is our, I'm not going to use the word, but this is the law, the theory that explains with more detail right now what our fundamental particles are and their interactions, how the fundamental universe behaves, and what are its components. So this is the table that you probably have seen already in many different contexts. But this was the view that we had in 1980. So turning from black and white to color. You can see here some of the particles, the fundamental particles, and the ones that don't have a cross, they have been discovered already. But those ones, for instance, the top quark, the tau neutrino, the electroweak boson, the Higgs boson, of course, that's the last one to be discovered. They hadn't been discovered back then in 1980. We didn't even know if they existed. And not only that, it's not only discovering the particles. We didn't know the properties of some of the particles that we already knew. We were not even sure that we would have 3 generations of matter, as we discovered a few years ago. There could be many others. So there was a long gap. There was a big gap to fill. So we needed to do research. And the way we do research with the instruments that we are using are particle colliders. So we use machines to accelerate particles at very, very high energies, collide them, and study their products, like you saw with Atlas. So the first time that this project, the Large Hadron Collider that you've seen already, was proposed was in 1984. It was actually a few years earlier, but the proposal was sent in 1984. This was the first time that we saw an image of how LHC will look in the tunnel of another accelerator that was being built at the time. It was a LEP accelerator, and this was the first proposal. So we were going to build a machine to collide particles at very, very high energies. And what happens when a collision occurs? When particles collide, it gets really messy because you're colliding, you're making the head up, you're making meet 2 particles that are not fundamental. Protons are composed of different quarks. And when you do that, a lot of other particles come out of the mess. It can get really, really messy. And the higher the energy, the messier it would be. So think about what you need to do. You need to, the particles that will come out of this mess will be very different one from each other. What would you need to do? Ask yourself if you want to measure everything that comes out of it. What are the needs of a machine that should be able to examine everything that happens in detail. Tell me, what are your guesses? Wild guesses. I can see the chat. Maybe I can see it here. Oh. Oh, this is a bit messy. Okay. So first you need to measure for each one of the particles that comes out of the mesh, you need to measure their trajectories. You need to know exactly where this particle left, what layers of the other detector the particle crossed. For each one of the particles, you need to know the energy they had. Because if you want to reconstruct the original collision, you need to know everything about it. So trajectory, energy of the particles, and of course you need to know which kind of particles you measure. It's not the same if you're measuring a muon, an electron, or a proton, or whatever. And you need to measure all of them. If some of them escape through the cracks of the detector, did they exist at all? If you didn't measure, you cannot know what the process looked like originally if you have lost part of the original process. So that's what you need to do. A big, compact, hermetic detector able to identify and to measure the properties of all the particles that you do. And you need to do it with precision, because if it's the precision of the ruler your measuring tape must be very precise, and it has to be fast, because the collision rate at LHC is 40 million collisions per second. So it's like a huge digital camera that needs to take 40 million pictures per second and do it with a very, very, very good resolution. So the way we're doing it is to organize it in layers, like an onion.
And can I ask a question?
Sure.
When you say to measure all particles, there's lots of detectors that would miss lots of types of particles. Like the LHC ones get a pretty complete coverage, but they don't get neutrinos. But if we think in the history of detectors, there were useful ones like bubble chambers that missed tons of different kinds of particles. So is detecting all particles a requirement, or just like kind of a wish list of something you'd want to include?
It depends on the physics you want to do. For instance, one of the detectors at LHC, it's LHCb. It's just like a section of a hermetic detector. It's only measuring the particles that go in one side. The idea of this detector is identifying a type of particle from the beginning and then see how they decay and see what they become. Obviously, for that, you don't need to reconstruct everything that happens in the rest. But in our case, we need to, one of them, for this Atlas and CMS, the two main experiments at CMS, you need to, one of the requirements is to impose energy conservation. Because the example you said is perfect. For instance, neutrinos, you cannot measure. Neutrinos is a type of particle that barely interacts with matter. So if you produce a neutrino in your collision, it will escape your detector. You will not see. The only way to identify that you had a neutrino there is reconstruct the whole process there and impose energy conservation, because you know that the particles, when they collided, and the balance of energy in this transverse direction will be zero, because they have if you sum the momentum of all the particles, the momentum of all the particles, it has to add up to zero. So if you have something that took all the energy in this direction, but something is missing in this other direction, then you know it was a neutrino that took it, unless you had a failure in the detector. So yeah, if you want to reconstruct the full picture, you need to reconstruct all the particles. That is a dream. That is impossible, because there are always detector inefficiencies. There are some particles that escape through the accelerator pipe. But the more hermetic you are, the less, let's say, indetermination you will have in this.
Thank you. And there's a question that came through in the chat. Do you want to read it, or should I relay it?
Sure. If it's, yeah, please.
So it's how big a team is needed if you're examining all of the tracks, and how precise is the detector to get all of the particles?
How big is the
The
second
team, like
category?
how many people working on it?
Well, the CMS, the experiment I work with, we are 3,000 people, over 3,000 people. Atlas is more or less the same. So these are the two largest collaboration, and LHCb is 1,000, so that's thousands of people. That's a lot of people, because each one of the layers I'm gonna talk about right now requires a lot of time and a lot of R&D and a big effort to put together. And the second question was how precise it was the.
Yeah, how precise is the detector to get all the particles? Or I think, but Vanessa can clarify if this isn't what's meant by the question. It's like along the lines of how many do you miss, or like.
It's hard to say. It's hard to say a number. The precision is one thing. The precision in the measurement is how far you act from the actual value when you measure. If you measure a particle in this direction, how can you be sure that it was here and not 1 millimeter to your left or to your right? That's the resolution of your detector. And what they are asking for is the efficiency, actually, the efficiency in measuring all the particles. That depends on each one of the layers. Each one of the detector has a different resolution and a different efficiency, but they are in very, very high values. And the efficiency is above 99% most of the time. So yes, you're gonna miss some, but in order to estimate how many, there will be simulations telling you how many did you miss, and that will become part of your measurement error after all.
And it's probably worth also reminding or clarifying that precision can mean multiple things. You can have the precision for each track where it went, but then we've heard a lot of people talking about getting more precise measurements of the Higgs boson mass or mass energy, and that's from statistical methods. And so if you're teaching, say, a high school physics course, because most of the teachers, you're teaching something, some of you teach physics, because particle physics is a physics topic. So this would be the difference if you're setting up an experimental setup, say for a pendulum experiment for students in class. If you're getting precision on the measurement for a certain number of pendulum swings, or if you're combining results from a large group, say a class or someone repeating the experiment a large number of times, and you can narrow down the precision with a large number of measurements. So you can look at that. I think that's a decent analogy to the two different precisions in the detector, but Jesus, maybe you feel different about that.
No, the different in our jargon it would be statistical uncertainty. So the more times you repeat the measurement, then you will have the smaller error. But then there's also the systematic precision that it's due to the characteristics and to the resolution of your own detector. So for instance, if you have a ruler that has the division in the ruler are 1 centimeter wide, your precision will be 1 centimeter. You can measure many times, but it will not be much better than that. So that this spacing in the ruler between the centimeter marks is related to the systematic uncertainty. So if your detector is not good enough and it's not measuring properly, it doesn't matter if you repeat this measurement many times. So yeah, it has two components. You need to be very safe of both components of your measurement.
And there's a couple more questions that have come through. Are you okay to keep taking questions now, or have we interrupted you for too long? We should save some for the end.
If they're somehow related, yeah. Otherwise, maybe we can skip them to the end or to the end of this part.
So I think we'll go to Marcos now, which was related to you were saying how many people work on the experiment, and he's asking, is the team working from places all over the world?
Yeah. No, look at me, I'm in Madrid now, and the experiment is in Geneva. So yeah, it's most of the members of the collaboration, and actually not in Geneva, because we can do remotely most of the tasks. I mean, the ones that are related to the detector themselves, you need to do their maintenance or data taking. They have to be on site, but for the analysis and most of the computing facilities, they are distributed all around the world. I would say out of the 3,000 collaborators, I don't think not even 200 will be on site in Geneva. The rest will are anywhere.
But a lot seem to travel back to CERN relatively often.
Yeah. Depends also on the kind of job you have. How close is your expertise to the detector? For people working purely on analysis, data analysis, they go to CERN mostly for meetings, but the actual need to be right there by the detector, it doesn't exist. I know some colleagues that never went down to the cavern where the detector is installed. So anyway, maybe we can leave this question.
And we'll get to Rodney's question at the end. If I forget, remind me of it.
Okay, we'll do that, because otherwise I will lose my thread here. Actually, I lost it already. I was going to tell you, yeah, we've been talking about these layers of detectors, and in order to measure everything that comes out of a collision, you place layers, as in an onion, of different technologies. Each one of them will be specially dedicated to measure one type of particle or one type of process. It's like having a big onion, but not all the layers are onion. You have one layer of onion, then you have one layer of potato, then we'll have one layer of watermelon, orange, and each one of them will be specialized in one type of process. So the central part will measure you will measure the energy of electron. You will measure where the charged particle tracks are. There will be components used to bend the particle, to measure the muons, blah, 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 blah. If you put all this together, you will see this is a half image of what CMS looks like. And it has, they call it the cylindrical onion, because it really has that layered structure for different particles. Back to the story of the detector. On 1992, the proposal of the accelerator was already set, and then it came the time to propose what I told you about, which will be the layers of this onion for the two main detectors. There were other proposals, but then they joined together and proposed these two big detectors. The Atlas collaboration, that's the one you saw already, and the CMS collaboration, that's the one I work for. They are complementary. They are different technologies, but they are trying to measure the same processes. And this is the first sonogram of the detector, of the first image we ever had of how the CMS detector would look like. And it's surprisingly similar to what the final result would be. You can observe this layer structure very well in a cylinder, but you see that there are different detectors, different layers of different stuff in baby CMS. We will focus on one of the layers, the external ones, the external layer of the onion. And that's used to measure one of the processes, one of the particles that come out of the collision. Those are the muons. So the outer layer, it's always, in all these type of experiments, they are the muon detector. A reminder, what are muons? Well, remember, maybe you don't know, so I will tell you. You remember this section of the standard model table. There is a type of particle called leptons. The quarks are the other one that I didn't picture here. They form neutrons, proton. Leptons are independent particles. You know very well the electron, the neutrinos you heard about, and the muon is like the heavy brother of the electron. They are just the same as electrons, only it's 200 times heavier. And there's the tau, that is 3,000 times heavier. What is the deal with this detector, with this particle? Well, the lifetime of a muon is about 2.2 microseconds. That might look like very, very short lifetime, but consider that in the world of particle physics, the lifetimes of particles of unstable particles are 10 to the minus 12, 10 to the minus 15 seconds. So in the world of particles, muons are very, very long-lived particles. Of course, they decay, but they can, since they are traveling at speeds close to the speed of light, they can travel long distances. For instance, a 2 GeV muon can travel over 13 kilometers. So these muons are crossing us constantly because there are lots of particles of high energy that collide with the upper layers of the atmosphere, and then they produce a cascade of particles. And most of these particles are muons. So we are being crossed by like, I think it's 1 muon per square centimeter per minute or something like that at sea level. If you go higher, it will be more. So we have muons all around us. At the energies that the muons of the collision experiments that are being produced, the main way, I mean, practically all of them, the only way they interact with the matter they're traversing is ionization. So they cross us and they ionize some of the gas, the atoms of our body or the material that they're producing. So they strip off an electron of our atom. Normally, these electrons are really small, so you don't have to worry. We've been showered by muons since we were born, but they are very present in our life. So what's the deal with muons in collider experiments? Since they interact only through ionization, it's very difficult. They're very difficult to absorb unless you put a lot of material. So they will cross all the layers of the onion up to the last layer, and then you can measure them. Then you measure the others in between. But also, if you measure something outside, it's probably a muon because all the other particles will have been absorbed. That is the beauty of these particles. They give very clean experimental signatures. So what is a muon detector supposed to do? We already figured out what the muon what the detector in general should we do. So if you replace particle by muon, that's what you need to do. You need to measure the muon trajectory. So you need a tracking detector, something that tells you where the muon has crossed. You need to measure the energy. In order to do that, since muons are charged particles, same as electrons, if you put a magnet, that you saw with Marco already with the bubble chambers. If you put a magnetic field, the charged particles will bend, will have a certain angle. It depends on the energy of the particle. If the particle has a high momentum, they will almost be straight, but if the momentum is low, they will curve a lot. And depending if they curve to the left or to the right, they will be positive or negative. So that way you identify the momentum of the muon. You need to identify that it's a muon, and as I was said, since there is so much material inside, the only particles that will escape all this material will be the muons. To measure them all, you need to make it as hermetic and as redundant as possible. So we have a lot of different layers measuring the same thing, just to be sure you're not missing anything. So what technology would you use to measure this detector? The chosen technology for the muon detector in CMS and in Atlas as well, but with a different type of, practically similar, but yeah, different one. Were gaseous detector. Can anyone guess why? Why would you think we used gaseous detectors? There is one main reason.
And don't be shy, either shout out with your mic or write in the chat if you have any ideas.
Yeah. We could use another type of detector, scintillating materials, solid state devices, novel gases. Any idea? Don't be shy, yeah. The reason is this: money. Imagine that the outer layer of such a big detector is a huge volume. You need to fill that part with some material that will cause an interaction with your muon and will produce some signal that you can measure. Solid detectors like silicon detectors or novel gases or all these other type of detectors are much more expensive. You need to fill a large volume with something that is relatively cheap. And those are gaseous detectors because gas is cheaper. That was the main reason. And that's enough. I mean, it's not that we are, I mean, you know, when you are designing a detector like this, you need to find a certain compromise with cost and performance that you need. For the resolution that we needed, these gaseous detectors were enough. What was the design? The design for the central detector, the resulting one was this type of detector called drift tube chambers, or DTs. What are drift? What is a drift? What is a tube? And what are the chambers? So tubes. Each one of these detectors is composed by one single detector unit that is a tube. It's a rectangular tube, like 4 centimeters thick, and then they're like almost 2 meters long. Each one of this is a detector. You stack them together in several layers of tubes, and they are arranged in these large boxes that we call chambers. So you have the tube chambers, and what is this drift thing that I'm telling you about? The drift is the principle, the detection principle of the chamber. This is the section of one of the cells. As you can see here, is rectangular. It's 4 centimeters, 4 times one, a little bit higher than 1 centimeter, and there is in the middle there is a wire. So you have to imagine a very tense wire crossing the center, like floating in the middle of the cell. It's not floating; it has supports on both sides, but it's tense, so it stays right in the middle. How does it work? This is filled with gas. It's a mixture of argon and CO2. Imagine that we have a muon crossing this gas. As I said, muons of this energy, they mainly ionize our gas. So across the path of the muon, they will strip off some electrons of the argon atoms. Since we have an electric field inside of this cell, if we didn't have an electric field, these electrons would be reabsorbed. But there's an electric field. So this electric field attracts the electrons towards the central wire, the anode. So they drift. They drift towards the wire. When they're around the wire, they are collected in the wire, and that is a charge pulse. So this is an electrical signal that it's collected at the end of the wire, and voila, you have a signal that tells you that the muon has crossed the cell. If we only measure that, we would know that the particle, the muon, had crossed this cell, but we couldn't know if they cross here or here or here or anywhere else in the cell. The funny thing about these detectors is we do not only measure that the pulse has arrived. We also measure the time it took for this signal to arrive from the moment the muon crossed the cell till it reached the wire. And why? Because we know very precisely the velocity of these electrons through the cell, through the drift cell. So since we know the speed, the velocity of the detectors, and we have measured the time, we know the exact point where the muon crossed the cell with a very, very, very high precision, almost 200 microns. So it's really impressive that with a 4 centimeter cell, measuring just the time, you are able to measure a point. So with this tube, with this measurement, you have 1 point of the trajectory. And this is like the join the dots riddle that you can find in the newspaper. You have different points of the trajectory of the muon, and then you join the dots, and then you know exactly the trajectory of your muon. There is a total of 250 chambers, more than 170,000 tubes in total. And then, so for each muon that comes from the interaction point and it reaches the outer layer, there are almost 50 points. So that's why I say it's very redundant, but that's what you want. That you don't want to miss any of the points. So yeah, if that explains why so many people need to work on this detector. So the volume is very high, but also the complexity of it all, it's tremendous. And back to history. Now that you know what the detector is made of, These are some pictures in black and white for I don't know. It's more dramatic if you put it in black and white. But in 1926, obviously there were color pictures. These were the first chambers that were assembled in Legnaro in Italy, or here in Madrid. We didn't get it right at the first design, so of course there was a first type of design. Then we discovered that the gluing was not correct. They changed the shape of the cells, the way they were glued together, the compositeness of the different cathodes and everything. So there were different prototypes that were built until we found one that was appropriate and it was valid for the production. And then in 1997, our final design was presented, and this is the technical document. And I just wanted to show you these two drawings were extracted from that book in 1997. This one down here, it's a scheme of how the detector will look like, which is also very, very similar to the final result. But this one also this is a simulation. Obviously, in 1997, we didn't have data yet, but we had simulation of the processes we were expecting. And the outcome was, as you can see here, what would a Higgs boson would look like if it was in this mass range. And this was what we call the golden channel, because you see here a lot of red tracks and a lot of a big mess of particle colliding. And whenever there are muons, the is very, very clear. So this is what the muon, this was what the Higgs boson would have looked like, and that was a simulation. In 2000, more or less, we started assembling the chambers. This is here in Madrid, but there were other institutes where they were doing the same process, only different shapes or different sizes of chambers. This is more or less in the middle of the production in 2002. That's baby me standing in front of one of the chambers, the first DT chamber that we built when it was sent to CERN. Also, it was not only Madrid. We also had an institute in Aachen in Germany and two in Italy, Torino and Legnaro. These were the 4 institutes where the chambers were assembled, and they were all sent to CERN to be prepared for the final installation. They were installed, stored here in this area, in the area of an old accelerator. There is a tunnel that's also very unique with longer hair. They're checking one of the chambers. Also, they had to be installed, of course. This, as you can imagine, these are more than 1 ton devices that need to be slid into these red pockets of the detector. That was not an easy task because the chamber was different. Of course, the process of installing that, it took years. That's also me when I was a kid in the middle of the detector. It was like a hamster in a wheel. Obviously, when they were installed, you need to go up with the cables to test them and dress them, and that does also something not apt for weak hearts, because if you have fear of heights, you need to go up with a bunch of heavy cables. This is a picture I took many years ago. Also, from the moment they were installed and started operation, of course, the maintenance of that detector, it took. We keep doing that. We keep fixing the problems of the detector every now and then. Those we have maintenance periods, and so an operation is. And this is a picture. This is now a real picture of what the detector looks like. This is the beam line. Collisions happen here. And as you can see, as I told you, this is very similar to what we had at first, our first scheme of the detector, how the way it was conceived. And then, of course, one of the main results that we obtained out of the detector was the discovery of the Higgs boson that was announced in 2012, and it was this is a picture of the announcement of the Academy when they announced the award to François Engler and Peter Higgs. And they explicitly mentioned that it was awarded thanks to the discoveries done at the Atlas and CMS experiment. And this is, remember the one I showed you that was in the proposal, the image of the Higgs due to the simulation was in the proposal. This is what a real Higgs looks like. So we got it right. That was the happy ending. That's the end of our story, but that's the end, of course, of season 1. This is the only season I've told you about. Season 2 and beyond are much longer and much more complex, and we don't have time to that because, as you can imagine, data are not taken magically. We need a long, huge team taking care of that. The formats and the integration of the detector with all the other layers of the onion is extremely complicated. Of course, the detector doesn't take care of itself. We need to be on top of it all the time and be aware of everything that's happening. It's working in a very harsh radiation environment. So the detector itself is being damaged constantly by the radiation producing the collision. So we need to replace and change the technologies every now and then. And the accelerator itself will be upgraded. We need to deal with the new conditions because we're gonna have a lot more collisions per second when it's upgraded. So of course, in the physics analysis, but this is a topic for a different talk because I wanted just to show you the story. I probably went much longer than I expected because what I wanted to show you now is the detector that we have here. It's what we call the muon telescope. As I told you, muons are coming from above constantly from the cosmic radiation. So it's a source of particles that we have for free and we can use. When the production of DT chambers finished in 15, 20 years ago, we had some leftover materials and we have a little of emptiness syndrome. We didn't know what to do with the material. So we decided, okay, what can we do with this leftover material? So instead of having this huge 2 times 2 square meter chambers, we decided, okay, why can't we do something smaller? We cut these tubes, we cut these tubes to much smaller and do smaller boxes that we can use them as portable muon detectors. And that is what we did. And that is what we have here at CMR, what we call the muon telescope. This is an image of the main components. Here you can see, you cannot see very well probably, but I'm gonna show you now, the 4 units that form our muon detector. Instead of showing you here, I'm gonna show you live. Let me stop sharing. Turn off this camera here and turn on the camera on my phone. So you can probably see the detector here. Also, I have another one, panorama. Oh, what happened? Okay, this is gone. Never mind.
Is your hand okay? I was gonna ask if your hand or something.
Yeah, sorry.
Now we see. Okay.
Okay. See, you have here the detector I was telling you about. Each one of these units here is one of the chambers. Well, you can call it chambers here. Each one of these has 4 layers of these tubes. You can see it probably much better here. This is one of the chambers that was assembled for show. It has a plastic cover just to see it. It would be very difficult to see in the video, but more or less you can have an idea of the tubes, the shape of the tubes. This is one of them. If you look very close, you can see, I think you can see a wire in the middle. It's a little bit darker than the rest. I think you can probably see it. It's tense. It's a bit darker because it has been there forever. So this is what a detector would look like. Of course, the good ones are closed, and it's a closed volume. It has been flushing water, gas for some time now. And we have 4 of these units. 1, 2, 3, and 4. And each one of them measures 4 layers. So we have, for each muon that crosses this detector, 16 points. So connect the dots, and you have 16 points in your trajectory. Of course, as I told you, this is a clock. What we are measuring is time. We're measuring the time it takes from the muon since it crossed the cell till it's reached the wire. So in order to know that a muon crossed the cell, we have this other system right here. This is a different detector, but it is also a particle detector. These black planes here are scintillators. When a muon crosses the scintillator, it also ionizes, but then the electron, the ionization electron, is reabsorbed, and in this process, it emits light. So the light goes to the end of the device, and these are other type of detector. This is a photodetector. It transforms the light into an electric signal. So we have 2 scintillators here and 4 photodetectors. That helps us that tells us when a muon has crossed all of it, and it has crossed our detector too. So now what we can do is turn on the photodetectors, and you have here the electronics that control the coincidences of the photodetectors. And as you will see, it will start counting when the high voltage of the detector reaches a certain value. There you go. Little by little. If the voltages are correct, should be okay. Yeah, you see? They're counting. These are the muons that are crossing now, our detector. Okay. So this detector up here is already working and counting. Let's turn on the other detector. I didn't turn it on because it's super noisy and within a control car here. I hope you can hear me when it turns on.
Yeah, if it's on already, we can hear you clear. It's amazing how good the noise reduction on Zoom can be for regular noises.
I'm glad it is, because it's really, really loud.
We hear almost nothing. Well, for the machine noise, your voice we hear almost fine.
Excellent, because this fan back here, as you can imagine, this detector here has been assembled with leftover electronics and leftover materials, so it's it's challenging, because we're trying to put together a detector with leftovers, but it's fine. So this power supply was also leftover from when I did my PhD, and it was super old by then. Even now, this is used to turn on the high voltage in the components and to create this electric field that will cause the drift. So, and this is low voltage for the electronic. So the detector should be able to, sorry, it's almost ready to work. For now, I will switch off here, and I will turn on again my camera here, and I will share my screen. Because now we can control the detector from here. Okay. This is the program that controls the high voltage of the detector. Of course, it's done remotely. So we're going to turn it on. Let's see how I turn it on. All 4 detectors. I'm going to do this as quick as I can, because otherwise it will be boring for you. Hilos mean wires, cathodes, strips. So these are the different components of the cell. And then we are turning them on till they reach the, oh, sorry, a little bit late. Okay. I'm gonna do it much quicker than I'm supposed to, because obviously we don't have time to observe. But as you can see, these are the different voltages of the different components and how they reach their values. It takes some time. What I'm gonna do now, while these voltages are reach their nominal values, is to turn off the.
And there's a question: is the interface on LabVIEW?
Yeah, it's all LabVIEW. Yeah.
Which I'm guessing is a software package to visualize things, right? Like
Yeah,
for those who don't know.
Yeah, thanks for that. Yeah, LabVIEW is software for controlling. It's a very standard package software for controlling electronics. So we are controlling now an electronic board that communicates with the high voltage supply. Now I'm going to turn on this other program. It's also live view, and it's communicating through an USB gate to the electronics that measure, that collect the signal that come from the detector. And there is a, let me check. And now I have to configure this electronic. This, if I remember correctly, was 1000, and this is 50, and if it wasn't, I should have probably checked it before. Okay, but we are going to configure this. We're going to see muons. Reactivation status, okay. There's a red button there, but probably it's only because we have the, okay, this is good. And let's try to take some data. Okay, yeah, we're fine. Here, you see, these are muons. These are the muons that we are taking right now as we speak. Each one of the light green boxes is one of the cells that has been crossed by the muon. You can see there is a lot of noise because we're turning it on, so the currents are yet to stabilize. So that's why we have some more noise than usual. But you can see very clearly the tracks of the muons. This is one of the super layers, one of the chambers, one of the other chamber, and they are perfectly aligned. Obviously, we have more. We need more statistics for this, and we do not only measure the box where it is. As I told you, we can also reconstruct very precisely in which part of the cell the muon cross. So we can reconstruct particles with very high detail. I wish I could show you now some software that have for reconstructing particles. But they are in maintenance. The platform where I normally run this code is under maintenance, and I just found out a couple hours ago. Sorry about that, but anyway, you wouldn't see much. You will see more or less that we have now. So yeah, we have turned on and operated the detector, and as you can see, we are observing real data right now. Let me go back to I had video that I recorded before here, just in case for some reason the detector didn't work. This is not real, but we were lucky, and we had the real thing. This is the video.
A quick question about this display. Is 1 and 3 in either the X or Y plane, and then 2 and 4 the perpendicular plane, like we're getting tracks in 2 different directions?
Exactly. In this display, they are aligned. So 1 and 3 here are aligned. Well, this is the video. It's not the real time, but it's the same. 1 and 3 are aligned so that the same cells will be crossed by the same particle. And the wires of 1 and 3 are perpendicular to the wires in 2 and 4. Actually, each one of these chambers, what we call here super layers, each one of this stack of 4 layers, they measure the projection of the track in one direction, in one plane, obviously, because the tube is long. You know which tube crossing which distance to the wire, but what you don't know is the exact point along the wire. But the fact that you have 4 different chambers with the wires perpendicular to each other, if you put together all this information, you can reconstruct the track in C. So yeah. So 1 and 3 are parallel, and 2 and 4 are parallel, so to say.
And looking at the display, it seems like a good time to come back to a question I didn't interrupt you with earlier when you were showing the detector as a whole. And that's what happens when one of the tubes stops working. Do you just not get information from that region?
You just miss it. You just miss that part. It can be for many reasons. It can be because the tube is damaged and it's not working and it's not connected. The cable that it's supposed to supply. Let me go back again to this camera because I can show you. I don't know if I. I don't know if you can see it because I can only see my.
Oh, sorry, I forgot to switch between which camera is spotlit, so no, most people won't see anything. So just a sec.
Okay, perfect.
Now
now
we
we're
should
back.
see what you're showing.
So this is how the high voltage is input to each one of the cells and each one of the components of the cell. Imagine one of these cables, one of these pins is broken or unplugged or whatever. So you will miss that cell. Imagine there is no wire because during the construction there was a mistake, there was a failure, there was a drop of glue right there in the middle, and you cannot operate that cell. So that will disappear. But the good thing about this is that it's extremely redundant. So we have 16 points to reconstruct the cell. You don't need 16. You would do just good with 2. So that's okay if a whole layer fails, if a whole super layer fails. That was the idea behind constructing such a redundant detector. I think we can, let me check if, that's probably not very interesting, but yeah, it's, if I turn the scope, no, it's broken, sorry. Never mind. Back to, whoops.
And there were 2 more questions that came in. One is it possible to replace a single damaged tube in CMS?
I have done it. It's possible. It's super complicated because in CMS, let's see if I have a picture of. I have a picture of CMS. This is not. Yeah. Oh, here you can see CMS. If you want to open one of these detectors, one of these chambers, you need to remove, of course, you need to remove this shield, you need to remove all the cabling, remove all the protections, open the chamber, but then you need to access not only this side, but the other side as well. And you need to go there with a wire hanging from one side. It's super complicated, but we have done it. Even replacing the wire in the chamber outside of the iron pockets is complicated. Inside there is a nightmare, but it can be done. However, you only done it in very, very special circumstances, because if you miss one single wire, it's not a big deal. You see, you have almost 50 points along the trajectory of there. Even, it's not the case, but even if a whole chamber is missing, there will be no problem. You can reconstruct the full muon track with almost the same precision. But it was designed in that way. It was designed so because accessing the detector when CMS is completely closed, this is not how the detector looks when during the operation time. This nose you see here, this calorimeter is inserted in here, so it's completely because it's inaccessible. You only can access it during a few periods. I mean, only during winter breaks, during Christmas breaks, and not all of the Christmas breaks. So we needed to be sure when we decide detector that even small failures or even more dramatic failures would not affect the performance. And actually, the drift tubes have been working extremely well since they were turned on.
And it was also asked, how long do you usually run the experiment to get significant results?
Which experiment here, the muon telescope or CMS? I guess they're referring to my setup here. Depends what you want to do. If you want to measure efficiency of the detector, you don't need much statistics. Maybe with a couple hours of muons, that would be okay. For other, I had a student last year. I had a student doing his master thesis with this. He did a fantastic job, and we took data in order to evaluate not only the efficiency of single cells, but also the efficiency of different positions along the cell, doing precise reconstruction and measuring rates. That took much longer. The longest one we had, it was almost 24 hours. But it depends on what you want to do. And it's also depending on the configuration of the trigger you have. I mean, the signal, the starting signal of your data acquisition, that for us is this device that I have shown you with the scintillator plastic. They're not very wide, they're actually quite narrow. So they are only triggering in muons that cross this narrow part. If we had another type of trigger, and we have that already in mind, we have an electronic that will be installed in the file detector that will use the data to tell us. I mean, the same data will tell you if it was coming from a muon or it was not. So the statistics will be much higher. It will be much faster to take data.
And there's more questions coming through, but seeing as it's getting a bit late, do you want us to hold them for the end, or do you want me to relay them as they come through still?
I probably just let me, I have finished actually with what I wanted to show here on site, but and I wanted just to give you three very fast tips for detectors that you can use in the classroom. Maybe you heard it before. If you have, just stop me, Michael, and I will go with it. But there are three options that I can give you if you want to use similar stuff to show your students how particles look like and what are the cheapest
that
one
sounds excellent.
Okay, the cheapest one is probably a cloud chamber. Cloud chamber, I didn't explain in detail. The principle is similar to the bubble chamber that Marco showed you, but it's much simpler. It's something that you can do, at home. Actually, you can do it with just everyday objects, with a can of beans, just just paint it in black at the bottom. So what you have here, it's a volume. Doesn't have to be closed, but it has to be more or less close, filled with alcohol, with isopropyl alcohol. And in that volume, you need to create a temperature gradient from the top to the bottom in a way that the region in contact with the bottom has to be colder than the other one. It creates a vapor, and the charged particles crossing that vapor create the ionized state, and around this ionization point, what you see is these little traces of cloud. So you can identify very easily particles coming from the cosmic radiation or from a small radiative source or whatever you have. And this is the only problem here. It's not really a problem because these are very cheap. The problem would be to find dry ice. That's not expensive, but you need to find something to. Dry ice is carbon dioxide. It's frozen carbon dioxide, and it's the temperature is minus 82 degrees Celsius. And that's what you to cool down the bottom part.
And for those of you who might be somewhere where you can't get dry ice, there are some other alternatives, but by far the most common classroom version uses dry ice. The two most common alternatives are using Pelletier coolers. There's a very good model one by a teacher in Spain, Juan Antonio Jimenez. I'll look for a link for that. It might take me a while, so I'll send it with an email for a future session. But if you can't get dry ice and you can order a Pelletier exchanger online, that's an alternative. Or Science Gateway at CERN has been working on one, and they've gotten it to work where they use a block of ice and they use, I think it's a reservoir of boiling water or hot water. Yeah. Because the bottom line is the temperature gradient needs to be big. Exactly. So you can play around with other things if you can't get dry ice.
Yeah. So if you can, as Michael says, the point is the gradient. So if you have regular ice, you have something really hot on top, like a heater of some kind, that will work too. But that technically, it's a bit more complicated than this. With just the dry ice, you will make it work. There is a link there where you can have the instructions on how to build it, and in a very simple way. And there is a lot of literature about this. So that's a very simple and beautiful way to show your student the tracks of particles, the ones that are around us, these cosmic muons that are easy to see. Another version, which is a little bit more expensive, but it's not that expensive, is this Cosmic Watch. This device is very similar to the, it's very similar. Actually, it's the same. It's exactly the same, but it's very, in much smaller size than the scintillator plastic that I've shown you that we need to tell us that there's a muon coming there. That's a scintillating material, particle crosses it, and partial particle crosses it, ionizes, emits light, and then you have a photodetector, the silicon photodetector in our case, because it's much, much smaller, and then it's all plugged in an electronic board connected to an Arduino with the software already pre-installed, so you can operate it very, very easily. I have here actually a stack of 4 of those. Let's turn again my phone camera, switch off this one. Michael, let's do this. Okay, thank you very much. So this is a stack of all this Cosmic Watch. These are off, but as you can see, they're simply plugged with a micro USB cable. Turn it on. Let's turn it on now, and you will see there is a light there that lights up every time a particle crosses it. It automatically measures the rate. You can do a lot of interesting measurements with it. You can pair them, so you can look for coincidences in 1 or 2 detectors, and you can use them to measurement the rates, the angular distribution of the muons. You put them in coincidence and try to see how the coincidence vary when they orient them differently. You can even take them on a plane and check the different of rate of cosmic particles as you are traveling, as you are going up in height. It's very, very interesting. These are a bit, I mean, it's not as cheap as the, as the cloud chamber, but they're not that expensive actually, because like, let me turn this off and go back to my phone camera again. If you have some minimal electronic skills and you can assemble it yourself, you can just buy the components and do it yourself. The instructions are there. And for 200 euros, you can get a pair of detector. It's not exactly cheap, but this is something you can keep in your school and use it for the future. So that's very interesting and something to consider, because there are many, many things you can do. The most expensive alternative is the mini Pix detector, but there is this opens the field for a lot of different measurement. I didn't bring any, sorry, I forgot. It's the size of a pen drive. Actually, you can just directly plug it to your computer. And here's our radiation detector here. It's based on the time Pix detector, which is a silicon pixel detector that measure very, very precisely the trace of ambient radiation, charged particles going anywhere. And like with that, you can do a lot of different experiments, not only particle physics, but also radiation protection, environmental issues, and a lot of stuff. And for that, there are many options and possibilities. Obviously, purchasing one of these maybe is not the best option if you're not going to use it. But for instance, here in Madrid, and I know in other places of Spain, the educational central services of the different regions, they have some of those that you can borrow for different experiences. So if you have any doubts, if you're in Spain, you can contact me. Probably in other countries they have the same, but you can borrow them to do different projects and use them as you wish. It's a good investment. Those are my 3 recommendations for particles detector that you can see very easily. Say use in different projects. But there are many other options. I wanted just to show you 3 from the cheapest to the most expensive of the family of particle detectors for the class. That's all I had to say. Probably we can go to the questions if we are extremely late. Sorry, I keep on talking and talking. I promised I wouldn't, but sorry.
Well, for me, I love it when you have interesting things and then you just keep going on. And for anyone who needs to disconnect because we've gone late, don't worry. I'll be publishing the recording sometime soon. As you may have noticed, I have problems with getting a good internet connection in Ghana. But the last week's session should be online by the end of this week, and this recording should be online probably this weekend or so. Just before we get to questions on the topic of low-cost detectors to do in the classroom, that's a perfect time to remind people of Thursday's session with Federico, who's on this session now, leading us through a homemade gas detector. So check that out if you want to find out an even cheaper way to detect particles in your room. Federico, I see you there. Do you want to mention how much you think it costs? Thinking of what you used, probably it's like the €10 range, but you'd know better than I do.
Yes, that's the money we spend. Of course, you have to find some some material that usually you can easily find at home. So maybe a few euros are enough.
Perfect. I'm really looking forward to that session. I hope everyone else is too. If anyone has questions, Jesus, you said you're okay staying on if there are a couple more questions, right?
Yeah, sure, no problem. I see a comment from Marco saying that it's not difficult to explain to security when you take this to the plane. Actually, it's super small. You can plug it to a power bank. Nobody would even notice that you have that. You can tell it's a very, very old-fashioned cell phone. Yeah, but I have seen measurements of rate as the change of rate as it goes in altitude. You can correlate it because it's actually you don't need to connect. You don't need to connect it to the computer or anything. It has a SD card slot, so it's recording automatically the measurement. So yeah, it's fun. I'll never try it on a plane. I'll let you know how it works.
And there were some questions in the chat that I said I'd get to at the end, but because a couple people have left, if you're still here, please repeat any of the questions you might have wanted to ask. And especially now that it's not interrupting anyone, be especially not shy to speak and with your microphone if that suits you. And to see if we have questions, and we won't keep it too long if there aren't any questions, but I have a couple, so I'll ask one of them. When you were measuring the trajectory as like finding the unknowns, you were saying from the magnetic field and the curvature, we can get the energy and the momentum. To check that I'm understanding that right, is that only because we know it's the muon and it's a mass that we can get the energy, and from other particles, we'd need it to be absorbed by a calorimeter, like something where we wouldn't be measuring the path, we'd be measuring the energy of the particle in that case?
Exactly. For the muons, it's simple because by the time they reach a muon detector, you assume it's a muon. Actually, maybe the first layers you can have some punch through pions that escape the whole thing. But if you have something that has crossed all the muon detection stations, it's for sure a muon. It cannot be anything else because any other particle will be absorbing the muon. And yeah, for other particles, you need to identify and absorb them. There's, especially for neutral particles, there's no way. You cannot bend them in the magnetic field. So you absorb them in calorimeters. So it's done.
And then there's a couple more questions in the chat. Are you reading them or do you want me to read them out loud?
I have seen, yeah, but you're keeping track of which ones I didn't answer. So yeah, please read them for me in case.
Okay. So do you experience noise from external particles that make detections difficult?
Noise from external particles. The only noise that you can have noise from external particles. There are different ways to say it. You can have noise from particles from the cosmic radiation. that doesn't make the detection difficult because first, because the detector is 100 meters underground, so it's the particles that reach the cavern are very energetic, but there are very few, and they are very easily filtered out because you need the we are looking for particles that point towards the interaction point. If there is a particle that it's crossing the detector, but it's not reconstructed pointing to the detection to the interaction point, you get rid of that because this is not a particle that comes from the collision. It's you will probably even pass the trigger requirement. So that's not part of the problem. There can be other type of problem that makes detection difficult. Is probably the neutron background in the cavern, considering that we have collisions that are happening all the time, and there is some fog of other particles, especially neutrons, that are in the background. This what they can cause in the external layers are a lot of noise, and this is not only the noise that makes the measurements difficult. It's also the problem that you are you're damaging those detectors, so you need to protect them against this residual radiation. So that's something that was done afterwards. This is something that we kind of underestimated at first, and we then realized that the outer stations were giving much more noise than expected, so we had to install some extra protection. So this is something you learn along the way. But they don't make, it's not that they make detection difficult, it's that they complicate things in the technical part.
And there's another question about how specialized the equipment is. So it's I see you have CERN equipment doing the acquisition. How specialized does the equipment need to be to use with cloud chambers and other low-tech demonstrations for high schools? I know the Cosmic Watch uses Arduino, but definitely LabVIEW is more specialized.
Yeah, for cloud chambers, you don't need any electronics. So it's not an electronic detector. It's also all visual, so you don't need anything. For the Cosmic Watch, yes, in Arduino. The software, you can control Arduino easily if you know a little bit of how it works. There is the kind you have seen are power supplies. You don't need power supplies for these detectors. They are powered internally through the custom board that they are using. For our detectors at CERN, we use CAN. Yeah, you have seen well. We have very, very old CAN power supply here. The one we're using in the detector is custom made. This is commercial, but the ones we have there are custom made.
And I think that's all the questions that have come up. And because we have gone a ways over time, I probably won't give it a couple more minutes to see if there's more questions. It's probably a good point to end things on. So this has been really great. I don't know if you've seen through the chat all of the thank yous and messages, like from Marco, who said he'd done this experiment or similar in university, didn't like it then, but loves it now. So it's
I missed that one. This experiment at the university. Oh, okay. I'm curious to see this experiment. Which experiment exactly? You have drift tube detector, similar drift tube detector.
So the one you did in your lab with the 4 layers of detectors.
Yeah.
So, and I don't know what we measured then. Maybe something about time of flight of muons. I had just this one and just thought, wow, I know that.
Yeah. I have I did one. Yeah, when I was at the university many years ago. We did the time of flight as well. But it was using the scintillator. It was using scintillators in estimate. Yeah, it was. I wouldn't say it was boring. It's always a matter of how they explain it to you.
But I did not understand it then.
Oh, that's
that was the problem.
Well, I'm glad that your opinion about this type of experiment improved.
So sometimes it only takes an excellent teacher, which coming from teachers, that's a great compliment and kind of a great note to finish on, encouraging everyone to keep passing things like this on to your own students as well. So thank you again, Jesus, for joining us and sharing all of this and inspiring us. And thank you everyone for joining in the fun.
Thank you very much, Michael. Thanks everyone for being here this time of the day. It was a pleasure. You have my, I didn't mention explicitly, but you have here my email in case you need any advice, any clarification, or whatever you want to ask me. And feel free to drop a line, and I'll be happy to keep encouraging you to use particle physics for the school. Thank you very much. Thanks, Michael, of course.